चलो we'll start okay, we'll just revise what we were doing last week. And so last week we started with, hopefully we'll be done with this. Okay? There's not a lot in transition metals. So anyways, last week what we were doing was we started with transition metals having colored compounds. Okay? So but before that we started learning about transition metal complexes. And I told you that when you have copper sulfate aqueous, the copper ions dissociate. And what happens is that there's a positive copper ion, and that +2 copper ion gets surrounded by a water molecule. So this one has a +2 charge in the middle. And you've got water molecules which are known as ligands. Okay, we wrote down the definition of what a ligand was. A ligand was a species that has a lone pair, and that lone pair gets attracted to the positive metal ion that's going to be in the center, in the middle. So all these water molecules are going to come in, and they're going to start sticking to the copper ions that are in the middle, and they're going to form a dative bond. You can remember this bond over here. This bond over here is a coordinate dative bond. So it's a dative bond or a coordinate bond because the lone pairs are coming from water. So the copper ions are not really contributing anything to it. So copper gets surrounded by water molecules, 6 of them. And this is known as hexamine 6. Okay, you've got aqua means water and copper 2 complex, and that's your blue solution. So the blue color of copper sulfate aqueous is not because of copper sulfate, it's because of copper ions being surrounded by water molecules. That's why it's blue in color. So copper ions surrounded by water molecules, that's CuH2O6 2 plus. So you have to remember a couple of these complexes. So we wrote down the definition of what a complex ion was, that it was an ion formed when a central metal cation datively bonds to lone pairs of ligands. And what's a ligand? It's a species which has lone pairs and can datively bond with a central metal cation. Okay, complete कर लेते हैं, forming a complex. So kind of the same definition, forming a complex ion. And then we talked about ligand exchange as well, or you can call it ligand substitution, which is that if a solution has water as the ligand, so water surrounds the copper ions. But if you replace that with some other ligand, for example, you start adding OH ions to it, then your copper will get surrounded by OH ions. And I told you that only 2 of them will surround it, because what happens after that is that after the first 2 OH ions, this becomes completely neutral. So it stops attracting the lone pairs from water because it's copper +2 and OH -1. They all get together, they end up forming a neutral compound, which is a crystal, that's CuOH2, and that's a pale blue breastplate. So CuOH2 is neutral, TK, all of that is written. Then I told you that you can add NH3. So when you add NH3 aqueous, what happens is that that the copper will then be surrounded by ammonia ligands. So it's going to start getting surrounded by ammonia ligands. And that number wasn't very specific. You could have 4 NH3s around the copper, or you could have 5 NH3. So I wrote down N, and H2O is 6 minus N, which means the total is going to be 6 ligands. But it's your choice. You could have a combination of NH3 and water molecules, or you could also have all 6 of them as NH3. That would be all right as well. And that's also an octahedral complex. There would be 6 of them bonded to it. And then I told you about concentrated HCl, that it could be surrounded by Cl lines. And in that case, only 4 Cl lines are going to surround it because Cl is much bigger in size. So you can't really fit a lot of them around it. So only 4 of them are going to eventually surround this. Uh, Bigger ligands, you can't fit a lot around them. That's why it's going to be a tetrahedral complex. The angle would be 109.5. It's going to be tetrachlorocopper 2 complex, but only 4 of them are going to surround it. Okay, and then, so there were these 4 basic ligand exchange reactions that you got to remember. And you also need to remember the equations as well. So we had started writing equations for the same thing. Okay? यहाँ तक clear है Rumesa, Hala, Isaac, is this clear?
Yes, sir.
ठीक है, एक second for this. ठीक है. So we'll just start writing the equations for the same thing. So I told you that copper sulfate, if you add NaOH to it, what happens? The OH ions, they come in, they knock out some of the water molecules over here, and they become COH2, and the water molecules, they get knocked out. The next one is, what if we add ammonia to it? Remember, these are the same tests that you did in AS in practicals. So copper sulfate aqueous again. Now, what's going to happen if I add dilute ammonia, NH3 aqueous is added? Now, when you add a few drops, what is seen is you get a pale blue precipitate. And when you add ammonia added in excess, then what happens is that the pale blue precipitate dissolves. Giving a deep blue solution. So remember, this is the same exact test that you already did. And if you remember this, you add a few drops of ammonia, you get a pale blue precipitate. If you add it in excess, you're going to get a very deep blue solution. So what's going on? Now, the first thing is, when you add a few drops of NH3, now we're going to write the equations. The first thing that happens is the ammonia behaves as a base. So ammonia behaves as a base initially. So your ammonia comes in, and instead of acting as a ligand, it actually starts reacting with water. And when it reacts with water, and again, that's kind of a reversible reaction, it becomes NH4 plus 1 and OH minus 1. So what happens is that the same ammonia, it actually ends up producing the OH ligand. So the ammonia basically turns into ammonium ions, and instead you get an OH ion produced. And what that OH ion then does is that it has CuH2O 6. Remember, copper ions are in aqueous state, copper sulfate aqueous. It's got, this thing has +2 charge. So the initial reaction is not with ammonia, it's actually the ligand exchange that's happening with OH ions. And when that happens, you again get a pale blue precipitate, which is COH2. Plus the 6 water molecules, they get knocked out. So that's your pale blue precipitate that's forming. Right, that's the first step. Okay, so what happens when you add a few drops of ammonia? The ammonia behaves as a base. It attracts the H+1 from the water, and then turns the water into OH ions, which then starts acting as ligands, and you get a pale blue precipitate. Now, the same thing when you add ammonia in excess. your pale blue precipitate dissolves. So your CuOH2 solid, now you start adding ammonia in excess. So let's say aqueous ammonia. So aqueous ammonia will have ammonia as well as let's say water molecules. Again, all of these are reversible reactions. They could happen in the other direction as well. So your copper now gets surrounded by ammonia again, and maybe some water molecules, or maybe all six of them could be ammonia. So you're going to get a +2 charge, and the OH ions are going to get eventually knocked out. And that's your deep blue solution. That's it. Okay, so this is what goes on when you add a few drops of ammonia and then when you add ammonia in excess. Now remember, this is all you got to remember. You basically have to remember what's going on when copper sulfate. So there are not a lot of equations, but these ones, I mean, they're just going to literally ask the same equation. Okay, the question will be exactly the same. Okay, what happens when you add a few drops of ammonia? You have to explain it using an equation. What happens when you add excess ammonia? You're going to write an equation. You're going to tell them this is what's going on. Okay, there's a Ligand exchange that's happening. It's been one thing you got to remember. There's one reaction which is not Ligand exchange, and that's where it's this one over here. This one over here with OH ions, that's not Ligand exchange, but this one is not Ligand exchange because COH2, that's a crystal forming, that's precipitation. A crystal gets formed, a precipitate is formed, so that's known as ionic precipitation or just precipitation. The other ones are Ligand exchange, where one ligand gets replaced by another one. Okay, उसके अंदर the OH one, what happens is that the ligands they eventually leave, and so that's not ligand exchange. Okay, so again, it's just this thing, and you just have to remember. You have to memorize basically this, that you have to know how to write the equation, and so there's one left, which is this one. So I'm gonna write the equation for this. Okay, when I add Cl lines, the water molecules they get knocked out, and Cl lines are going to replace it. So this is the last equation we're going to do. So this one is that so again you got CuSO4 aqueous, and concentrated HCl is added. And when you add concentrated HCl, a greenish yellow solution is formed. So this one is CuH2O6. Okay, that's your copper. I'm going to add HCl, so that's Cl minus 1. And the Cl ions, because it's concentrated, they're going to knock out the water molecules and they're going to surround the copper, CuCl4. Cu is 2 plus, Cl is minus 1. So in total, the overall charge is going to be minus 2. And the 6 water molecules are going to get knocked out. This one is your blue colored solution. This one, I mean, that actually is yellow, but CuCl4 2 minus. That's yellow in color. But you're going to see a greenish solution because some of the yellow complex, and there's going to be some blue complex that will be still left, and yellow and blue they combine to form something that's going to look green. So in reality, it's not going to be perfectly yellow, it's going to be greenish yellow. Because there's going to be some blue complex that's going to be left in the solution, and that's going to make it turn green. Yeah, that's your last equation. So yes, are clear? So this is stuff that you just got to memorize. Is that clear? Saro, clear? Omar, Ibrahim, Mesa, is this clear? Sark, is this clear?
Yes, sir.
Okay, I'll share the notes. So there's just these four equations, and they're going to ask you to, and they're going to ask exactly the same thing. अच्छा, अब ये कि you have to remember exactly the same thing for cobalt as well. For cobalt, the reactions are kind of exactly the same, but the colors are different. So which is why they got. So I'm just going to write that it's going to be exactly the same for cobalt complexes. Again, what am I talking about? I'm talking about the same reactions. Even the drawings, even the complexes, etc. They're all going to be exactly. They're going to be exactly the same. The only difference is that the colors are going to be different. The colors of cobalt are slightly different, and I'm going to, instead of writing all the equations, I'm just going to tell you what the colors are for cobalt. Okay. So for cobalt, the colors are, I mean, remember the complexes of cobalt, they're exactly the same. So there's CuOH twice. H2O6. Or concept Cu with ammonia. Two plus. Okay, so this one, with this one is brown. Okay, so exactly the same equation. You're going to write exactly the same equation. With Cl, it's going to be blue in color. With water, it's going to be pink. And the CuOH2, can I just give me 1 second? Green or just the latest market scheme. Just 1 second. Let me open the latest market scheme. With cobalt, 1 second. It used to be green, but the recent one wrote blue precipitate. Just 1 second. BPD color 9701. It's blue. The recent one is blue. It used to be greenish blue, but blue precipitate. Okay, the other ones are all solutions. The first one, that's blue. So remember exactly the same exact equation for cobalt. The only thing is that the colors are different. Okay, so you got to remember those as well. But the equations are exactly the same. Okay, so there's a little stuff that you got to remember. You clear a cobalt ke liye, it's exactly the same equations, exactly the same complexes. Only the colors are different. Is this clear? Hala clear, Rumesa. Ibrahim, is this clear?
Yes, sir.
अच्छा आगे ये कि we're done with the colors. You got to also remember one point is that that ligand exchange reactions are reversible reactions. So one thing is that all these ligand exchange reactions, the Le-Chatelier principle applies to them about equilibrium shifting to the right or left. Which I'm not going to go into detail because you already know what this is, that if you try to increase pressure or decrease pressure, if you try to increase temperature or decrease temperature, you know the rules that if you increase temperature, endothermic is favored, decrease temperature, exothermic reaction is favored. So all of these are reversible reactions. So if I look at any one of these reactions, uh, they could go in the forward direction, they could also go in the backward direction. For example, if I add more ammonia to this reaction over here, if I add more ammonia to it, the equilibrium will shift forward. It's going to try and decrease the concentration of ammonia. Vice versa, if I add more OH ions to this, the equilibrium is going to shift backwards, and that will produce more of this pale blue precipitate. As यहाँ पे I'm going to add this was your blue solution. This was my pale blue precipitate. So the same applies to pretty much all these equilibrium reactions. You add more water to this, the equilibrium is going to shift backwards, and your solution is going to turn blue from yellow or yellowish green. Similarly, if you add more Cl lines to it, it will shift forward and it will produce more of this yellow complex or the greenish yellow complex. Okay? So you be clear that the same stuff applies, the same equilibrium things apply to this as well. Now, apart from that, since these are reversible reactions, another thing that applies to them is the equilibrium constant. That also applies to it. So equilibrium constant Kc applies. And what's Kc? Kc is the product concentration divided by my reactant concentration. I mean, that's what Kc is. Except that Kc will have a different name. It's going to be called K stability or K stab. This is going to be called your stability. It's going to be known as your stability constant. So that's K stab. And by definition, what K stab is, that it is an equilibrium constant. You can remember it's the same Kc, except that it applies to ligand exchange reaction. So it's an equilibrium constant for a ligand exchange reaction when a complex is in equilibrium with its aqueous solution. So there's a limitation that the complex has to be in equilibrium with its aqueous solution. So it's the equilibrium constant, right? It's basically your Kc. When a particular complex is in equilibrium with its aqueous solution. So I'm gonna pick. So water has to be there. So I'm going to pick this reaction, and I'm going to write the Kc for this, or the expression of Kc. I mean, it's not going to be, you're not going to get a very complex question on this. So for example, and they could give you any ligand exchange happening. There are infinite number of ligand exchange reactions. The ones that we wrote above, those are the ones that you have to remember. But otherwise, they could give you any complex and any ligand exchange reaction. So here I have a ligand exchange reaction. I'm going to write the Kc or the K stab expression for this. So it's simply going to be the product concentration divided by reactant concentration. So it's going to be CuCl4. 2 minus, remember the square brackets, they represent concentration now. So now the charge has to be written inside the square brackets. I mean, this square bracket initially represented the complex itself. But now what you're going to do is you're going to put the charge inside the square bracket because that shows that the square bracket now represents concentration. So then you have water concentration, that's power 6. Divide that by my reactant concentration, so it's going to be CuH2O6. And 2 plus, I'm going to write inside the expression, and I didn't balance the equation, so there's 4 Cl minus 1 ions. So it's going to be Cl minus 1 power 4. The only thing you've got to do in this expression is you don't write water when you have an aqueous solution. So water is in large excess. And therefore its concentration would almost be a constant if more water gets produced, because water is in such large excess that its concentration would barely change. So not written in the expression. So that's simply what K-stab is. They're just going to ask you to write the expression, maybe find the units as well. So it's not going to be that difficult. ये clear सारों को? Isaac, is this clear? Rumesa, Hala, is this clear? Umar, clear? Ibrahim?
Yes, sir.
Yes.
So all these Ligands exchange reactions, they have a K-stab. So what does the K-stab tell you, by the way? It tells you whether Ligands exchange reactions are possible or not. So if you have a large value of K-stab, especially when you have K-stab that's greater than 1, that means it's favoring the products. That means Ligand exchange will happen. Well, a lot of times what happens is, I mean, you must have seen in the lab that you add something in excess and the precipitate does not dissolve, right? Kiska precipitate dissolve नहीं करता था, I think, like iron hydroxide, let's say you add ammonia to it, the precipitate did not dissolve. That meant that the ligand exchange was not being favored. That means maybe the derivative bonds formed over here between copper and water was so strong that even if you add concentrated Cl ions to it, the ligand exchange does not happen. So that means K-stab is going to have a very low value. Large K-stab means that it will favor the products. It's going to move forward, and you're going to have more products. You're going to have a bigger numerator in that case. So large K-stab greater means ligand exchange will happen, and that means the product complex is going to be more stable. I mean, whatever the complex that's getting formed is more stable and more likely to be formed. So they're going to give you, we're going to do past papers. They're going to give you different complexes, and they're going to ask you what's going to happen if you add a particular, you would have to predict, like if you add CLNs and this K-stab has a very low value, then you can kind of predict that this complex is not going to be formed. It's going to be this complex that's going to be forming. So that is one thing. K-stab means more product would be formed. It means more ligand exchange will happen. Okay, so that's all about case tab. You won't get a very difficult question on this. So, but is this ये clear है? Case tab clear है सारों को? Hala, Rumesa, Isaac, is this clear? Case tab. Ibrahim, Umar, clear है?
Yes, sir.
आवाज आ रही है? चलो. So now the next thing is, that's all about case tab. I'm going to do bidentate ligand, etc. later on. But the important question is, at least we'll do the introduction, which is why, I mean, there are two questions that are going to be asked. One is, why are transition metals colored? And the second question is, why do different complexes have different colors? So the first question, why are transition metal complexes colored? That's question number one. Again, that's a typical question. It's going to be asked in every paper. And it's got a very typical answer as well. I said, but before we move on to transition metal complexes being colored, it's all because of the d-subshell. There's something going on with the d-subshell. So we need to understand what the d-subshell is. So it's to highlight कर लेते हैं. So we got to understand what a d-subshell is. So d-subshell has 5 d orbitals, and those 5 d orbitals are, remember, you'll be asked to draw these as well. Okay? So that's why it's important. Like in AS, you were asked to draw px, py, pz. These d orbitals are dxy. There are dxz. You have dyz, and you have dx2 minus y2, and then there is dz squared. So in total, you got 10 electrons in this. So 2 electrons each. And that means you got a total of 10 electrons. Now you'll be asked to draw these. So learn how to draw this. So let's say this is my x-axis, this is my y-axis, and I've got a z-axis over here. And let's draw all 5 of them. Here that's there's actually 2 ways of drawing this. And here's my 5th one. So starting with the first one, the dxy. Now remember, in a d subshell, the electron density is spread out in 4 lobes. So if this is your x-axis, this is your y-axis, this is your z-axis. The dxy means that your electron lies between the x and the y-axis. You just let me. Okay, so imagine that the electron density lies between the x and y-axis, so it's in one plane. There's no electron density on the z-axis. There's no electron density above or below this plane. So it's all in the X and Y plane. So I'm going to write that it's in the XY plane. And it's between X and Z axis. So that's the first d-subshell. Electron density lying between the X and Y. The next one is DXC. Now, this one would be in the XZ plane. And you can think of the electron density being between the X. अच्छा यहाँ पे Z कर दिए. Sorry, this is Y. So over here, it's going to be between X and Z. So we're going to do that. So this is my Z-axis, this is my X-axis, this was my Y-axis. So now the electron density is between X and Y. So we'll also adjust कर लें. Okay, so hopefully that looks like it looks like the electron density between the X and Z. And similarly, you've got two others. You've got एक और draw कर लेता हूँ. You've got D. So we got XZ, XY, and now there's going to be YZ. So which one? You got X, Y, and Z. And your electron density is going to be between the Y and Z axis, so it's going to be somewhere. So between the Y and Z. The Y and Z, this is Y and Z, and it's going to be on this side and on this side. I'm going to just copy paste pictures of this. But the idea is that the electron densities are lying in a certain plane, and you will be asked to shade that area. Okay. Last two I'll do in the next class. Like, is this clear how the d-subshell looks like? That you got electron densities and it's in 4 lobes, and it's the orientation of the lobes, just like the px, py, and pz. The orientation of the lobes. Sometimes that lobe or the electron density is on the xy plane. Sometimes it's in the xz plane. Sometimes it's on the yz plane. And then there are 2 other planes which we'll talk about TK in the next class. Yeah, the clearest सारों को.
Yes, sir.
Yes, sir.
So remember this is important because they're going to ask you to sketch this, ठीक है? तो चल ठीक है, कल continue करते हैं with the same thing, ठीक है?
Thank you, sir.
Okay, take care, Allah Hafiz.